Hi there, my name is Vebjørn. I am a computer science student at NTNU in Norway. I'm graduating in 2026 and I'm currently doing a specialization in computer vision. So I wanted to make this video about an object detection model, which is called end-to-end object detection with transformers. This is a method that was released in 2020 and its iterations are currently the state-of-the-art methods now. So I thought it would be helpful to make a video where I code this model from scratch, showing you all the details about how it works under the hood with very minimal abstractions. So specifically, I will go in a top-down fashion in coding this model. So instead of beginning at the backbone, I will instead begin at the loss function. If we scroll down to the architecture of this model, we can see that it uses a transformer in its architecture. And I think this is really what makes this a milestone. That was the first model to introduce the transformer into object detection. It also uses a clever loss function, which uses bipartite matching to enforce unique predictions. So when coding this from scratch, we will first look at the loss function and then we will work our way backwards through the architecture. So we'll begin with the loss function. Okay, so scrolling down to the section on the loss in the paper, they say that the model DETR infers a fixed size of n predictions. So essentially that means that given an image into the model will always output 100 predictions or n predictions. They use n equals to 100 here. So like regardless of the image, you will always have n predictions and that's fixed. And then during training here, they say that they use bipartite matching between the predicted and the ground truth objects. And then after that, they optimize object-specific classes. So there's two steps here, really. One, we find the bipartite matching. That means like the optimal matching. We will see an example afterwards. And then for when you matched a predicted to a ground truth, then you will do backpropagation on that sample. So what this looks like on an image is essentially this. So you have a lot of boxes given a few objects. So in the paper they say that n, which is the number of boxes they predict, should always be significantly larger than the objects in the image. So we see here that there's many candidate boxes for one object. And how do you choose which box is actually predicting the object? So the way they solve this problem is by using bipartite matching. So in this example, you have that you're matching applicants to jobs, and you have as a rule there can only be one job per applicant. If you're familiar with the graph theory, that's essentially the same as one node can at most have one edge connected to it. We can also view this in the lens of DETR. So we can think that this is predictions and jobs are ground truths. So when we do 100 fixed size predictions, we want to match each prediction with each job. And then we want to calculate a matching cost. That's essentially a metric that is telling us how good of a fit is that box for the object. And then that will be the weight of the edge between the prediction and the ground truth. So, and then we want to find the matching between applicants or jobs, or in our case, predictions and ground truths. That's minimizing the overall cost. So we can go ahead and translate this into code now. So we have, as previously said, we have n equals 100 predictions always. And we have that one prediction here consists of a box and a class. And the box has 4 coordinates, and the class, well, the class is determined by a probability distribution over all the classes. So it will be like a discrete probability distribution. In our case, we will have 21 classes. So we can go ahead and first define the predicted box or boxes. So right now we'll just initialize those as random numbers because we don't have anything that actually predicts the boxes yet. So we just go ahead and say n and 4. And then for the predicted logits, we go ahead and say n and 21. So the reason that I say logits here and not probabilities is that to keep the training more stable. So when we have a fresh initialized network that we initialize from random weights and we begin training, we have that the vector of numbers that you get, in this case 21 numbers, you can have a tendency to have extreme values in that vector, and that will cause the softmax to converge to that entry in the vector. And that will effectively lead to vanishing gradients and a more poor training than you otherwise would by using techniques that you have in loss functions that actually expects logits instead of raw probabilities. We will come back to that later, but yeah, that's brief on why we have logits here. So that's what we predict, and then we will have some ground truths to match this with. So in this example, let's say that we have 4 ground truths, and our ground truth boxes will be of shape number of ground truth boxes and 4. And then we will have, for the ground truth labels, we will have 1 label per box. So that makes it this shape. So this will essentially be the input to our loss function. Now going back to the example, now as we have our input, we have our predictions and our ground truths. So we now want to make this loss matrix that computes the cost between each prediction and the ground truth. So we can initially just go ahead and define this. And we want the shape to be a number of ground truths elements, so that will be our rows, and then we will have our predictions, which will be the columns. So the shape will be ground truths and n, like that. And now we can populate this matrix. So what we can do is just to iterate through each entry of the matrix. And for each entry in the matrix, we want to compute the cost between ground truth I and prediction j. So we will have L matrix, our loss matrix, and then entry ij. We want that to be the matching cost, which we will define later, and our matching cost will take in our let's see, yeah, our ground truth boxes, ground truth labels, the predictions, and yeah, that should be it. So this is essentially computing. If we go back here, it's taking the object, and then it's taking a box, this one for example, and then it computes how similar they are by using a matching cost. And now we will just go through this loss matrix, go through every row, and then calculate the cost compared to every prediction. So how do they do this in the paper? We have, yeah, so this is what we're computing essentially. So we have the matching cost, and we can see that they define this to be here. So what does this tell us? They take the probability of the ground truth class, and they take the negative probability. They say that they do not want to take the log probability as common because they essentially want these two terms to be equal. So yeah, they take the probability and then they take the box loss. So this is making up the matching loss. So we can go ahead here and define the matching cost. So we now have a function that takes our ground truth box, label, predicted box, and predicted logits as expected from here. And we can start with the probability term. So now notice that the predicted logits will be a vector of 21 shape, and we want to turn this into a probability for the ground truth class. So we can go ahead and do a softmax to achieve that. So we have the probability will be plogits dot softmax, and yeah, by convention the dimension will be so there's only one dimension here, so it's strictly not necessary, but for readability it will be the last dimension, so that's over the columns. So this is our probability. So going down, we can define the total loss. We can start by defining that here. So it will be negative probability, as we can see here. But notice now that even though we have converted this into a probability, this is still a vector, and we want the probability for the ground truth class, which will be the ground truth label. So we just put that in here, as this will give us the entry which is corresponding to the probability for the ground truth class. So that was the easy part. Now it's the box loss here. And when defining the box loss, they are it's the intersection over union loss and the L1 loss, or a Manhattan loss, if you are familiar with that. So in the intersection of union loss, basically what that is that you have your predicted box and your ground truth box, and you measure how much they overlap. So in this example, you take the intersection of their overlap and then you divide that over the union. So you can see that the more these boxes overlap, the bigger will their intersection or union be. So like intuitively, the loss will be 1 minus the intersection of union. Except from that, they say that they use the generalized IOU loss because that's a scale invariant version of that. So we can go ahead and have a look at how that looks. So this is just a built-in function in Torch that we can use. So the loss takes in the boxes. It can either be of this shape or this shape. In our case, we only have one box, so this will be the shape we will be inputting. And there's also one more part to it here, and that's both set of boxes are expected to be in this format. And this format is essentially that there's multiple ways of defining a box. The format that this loss expects is that you take the upper left corner and the bottom right corner, and those 2 points will define the loss. Now, we do not predict the boxes in this format. So maybe you can think of why we don't do that. So one intuitive idea why we do not do that is when you have a freshly initialized network, the network doesn't have any sense of how the coordinates of the boxes should be output. And you see in this format, there are some constraints on the entries in the box. And this constraint right here, because you have a upper left corner, then you have, say for example, some constraints on the x coordinates. That constraint right there is very likely not to be satisfied when you have a freshly initialized network that doesn't know anything yet. So we will have to convert the dimension, the boxes that our network will output, which will be a center coordinate and then a height and width. We will have to convert that into this format. So we can begin with defining the IOU loss. So let's just say L IOU equals to this, and we see it takes in box reduction that's irrelevant to us, and also a epsilon to avoid division by 0. We don't need any reduction because Rn is 1 here. So we will just have our two boxes into this function. Our two boxes, they are the ground truth box and the predicted box. So let's just do that. And now, moreover, you have the L1 distance as well. That goes into the loss, and we can also look at the torch implementation of that. So yeah, pretty straightforward. You have your input and target. Let's see, do they say any shapes for this? No. Maybe if we go in here. Okay, yeah, so any number of dimensions that should work to just put in the same as we do for the IU loss then. So we can go ahead and implement the L1 loss. Okay, it looks like that. No. Okay, there we have the reference that we want to make. So going ahead and just L loss L1, and we want to refer to that as L1 underscore loss. And here as well, we just take in the same. Double checking that. Input, target, and yeah, the reduction here is also not relevant for us. Okay, so that's the two components of the box loss. We also see that they are weighted by some lambdas, where there are hyperparameters. Later down in the paper, they actually define these parameters. I have them here. So yeah, let me just copy paste that. So we have some hyperparameters that goes in there. So we have a hyperparameter for lambda 5 and the intersection of union 2. So we can go ahead and define our total box loss. Yeah, let's just keep the naming the same. To be L1 lambda times the L1 loss plus IU lambda times our intersection of union loss. Okay, so let's see if we got that right. Yeah. So then we can go ahead and see. Yeah, so we take the negative probability and then we just plus the box loss. So over here and then L box. So yeah, there we have the matching cost that goes into computing the similarity between a ground truth box and a predicted box. Now, one part that I almost forgot was that we have to be aware of which formats the coordinates are in. So our predicted box will come from our model. And as I previously told, this is the shape of the predicted box. So you have a center coordinate and then width and height. But we want the output format to be this coordinate, which is the upper left corner and the bottom right corner. So yeah, as this is very common when working with object detection, there exists a library from that. So we just import that from Torch Vision. And yeah, it's as simple as this. We just input the box that we want to convert, which is the predicted box, and then we redefine that. Okay, so I think that makes us ready to do a small sanity check here. So this should run now, but we have GT labels not defined. It's because of a typo, sorry about that. Let's try again. And we also want, yeah, okay. We want the data type of the label to be, so this data type is probably a float. Let's just verify that. Dot D type. Yeah, so we have float 32, but we want this to be an integer since it's basically an index in our probability distribution. So now, and yeah, of course, random numbers won't work. So let's just do ones here. And we would have to do D type equals integer. L1 loss not defined. Okay, that is because, let's see, yeah, it's a torch.functional, and yeah, we are just saying L1 loss, so we should have f.L1 loss here. And there we go. Okay, so we've now implemented the matching cost right here, which is defined here. So before we conclude the matching cost or the matching loss, let's have a look at indices. So we have CI not equal to empty, and CI is defined up here as a ground truth label. And the reason that we have CI not equal to empty here, you can interpret it as this loss is only computed for labels that are not encoding no class. So for the classes, we have our original set of classes, but in this model we also append one extra class that the model can predict when it doesn't think there's anything in the image. So it's an empty class, no object class. So this right here is basically telling us that the matching loss is computed over the ground truth classes that's actually an object. And by going through all the ground truth boxes, so we have our matrix where we have ground truths and predictions. If we only have ground truths on the rows, this will be taken care of for us. Because we will never compare a non-object to a prediction doing it this way. So we can now go ahead and find this optimal permutation right here. So the library that we'll use for that is one from SciPy. So it solves the linear sum assignment problem, which is the problem we are looking for. So the input will be the cost matrix of a bipartite graph, which we have just made. And it also has another parameter, whether we want to maximize or minimize. So this is set to false by default. So yeah, we can just leave it as is. So I think before going ahead and implementing it here, let's go ahead and do an example. So let's just take this. I've already imported it here. So let's just take this and do a toy example of it. So let's say that we have a 3 by 3 matrix. Like that. And let's check what M is. So a 3 by 3 matrix like this. And what happens when we call our bipartite matcher on it? We see that we get a combination of rows and columns. So this is basically one entry, 0, 0, and then 1, 1, and 2, 2. So we can now go ahead and see how this is affected if we change this. So currently we have lots of solutions to this problem, because every one of them adds up to 12. Say for a diagonal here, it's 12, for example, and the vertical line here, that's also 12. So we have multiple solutions, but what happens, for example, if we set the upper corner to 100, for example, in this example? How does that affect things? So you can see now we have 100 here, and that changes the optimal matching. So before we had 0, 0, so the optimal match was here previously, but now it's changed to here. So yeah, that's short on how this works in practice. So let's go ahead and implement it. So we have our optimal rows and columns to be our matcher on the loss matrix. And let's see what we have. Okay, so we have a bug here. Invalid numeric entries. Okay, yeah, we forget to return the actual loss. Let's try again. And there we go. So we have that for these ground truths. So for ground truth 1, it was the 87th prediction, and that had the lowest cost. For ground truth 1, it was the 77th prediction that had the lowest cost, and so on. And by the lowest cost, it's the matching cost that we predicted here. So in terms of that, so prediction 97 was the best prediction for this ground truth. So now what we can go ahead and do. So really this is step 2, compute the loss. And what we've done here is to find optimal matching. So to compute the loss, we can go down here, and here they have the actual loss that we will do back propagation on, and we see that given the optimal permutation that we've found here, they compute the loss as following. So they now take the negative log instead of just the negative probability, and then they take the box loss. But there's one important thing to notice here. In the matching cost, we only computed this cost where it was an actual label, but here we wanted to compute it over all the labels. So this is This is to provide more signal to the predictions that did not get included here in the matching. If we go over to our matching cost again, I'm sorry that these have changed the indices now, but that's because I ran the code again and we're using random numbers without a seed. But the thing is that if we would do backpropagation on this, only 4 of the 100 predictions would actually get feedback on what they predicted. And there's more feedback to give here because so these predictions actually predicted correct, and that's good. But for the other 96 predictions, we want them to understand that they should predict a no class. And that is why we remove this restriction there. So we all the queries that did not get matched to a ground truth, they will get included in the loss based on how good they predicted the no object class. And this is really how the DETR model learns to have unique queries. Now we can go ahead and compute the loss. Well, firstly, observe that the sum here, it can be split because here we have the class loss and here we have the box loss. So if we divide this sum into 2 about here, we can focus on this part of the sum first. So here we take the basically the negative log likelihood loss over all the predictions, and by default we can say that you are supposed to predict no class. So let's just go ahead and encode and code the ground truths, and then we will modify it slightly afterwards. Of length n, which is 100, and then times 20, as 20 is no class. So let's just check targets like that. So just a tensor of 20. But here's the catch. Now for some queries, we want to predict another class. So specifically, if we now print again the row and the columns, we want to predict for these predictions, because these got matched to a ground truth. We want to predict a different label here, and we want to predict the label to the associated to the ground truth. So what we can do now is to say that targets, and then we can index targets at the columns. So this will modify index 56, 61, 35, and so on of targets. And then we can set that to be the labels of the ground truths, and those are defined up here. So it will just be ground truth labels, and we'll index those by the row. Essentially, since the rows here are of size 4, and so is the labels, and it's in increasing order, it's basically the same as doing this, but to be safe, in case this would change, we index it by row. And now let's look at targets again. Okay, we have an index here. We want source and D type to match, but got float for the destination and long for the source. Okay, so let's set the D type of targets to be the D type of ground truth labels. That should resolve the issue. because the issue was that this D type was different from the labels. So when we tried to change the value in the targets to another D type, that would cause an error, because for one tensor, every one of its content must have the same D type. But let's try again. And we had a result there. So what we see here is that the targets are still all 20s, but in some positions we have a 1 and a 1 and a 1. So specifically for 4 of the positions we have a 1. And that is because here we set all the labels to be 1, like this. We could also take and set this to be, for example, a range from 1 to 4. And then we can see that our labels are 1 and 2 and 3 and let's see, there should be a 4 here. Oh, sorry, no, there should be a from 0 to 3. So 0, 1, 2, 3. We have all of them. So now we've changed the targets for all the predictions. So now if you give a set of logits for the predictions, we know how the targets that we want them to predict. There's also one slight detail they mentioned in the paper, and that is that they downweight the log probability term when the class is no class by a factor of 10. So the way we'll do this is to have a weights tensor, which will just be of size 21 or 20, and then we set the last weight to be 0.1. So then we have that the last weight is a factor of 10 smaller. So let's just check out weights. So they'll look like this. Okay, so now we have a set of predicted logits over here. So let's just check the shapes. So this is our logits. So we have 100 of them and they're size 21. And now let's check the targets and the weights. So what do we have here? We have 100 logits and we have a target, a ground truth for each of the logits. And then we also have weights. So when we compute the loss based on which class you are predicting, we are having a weight for that class. In this case, we'll only have a factor of 10 smaller weight for the last class. So now we can go ahead and we'll use the cross entropy loss. So we'll have our input and target, and we'll input our weights here. And this will, let's see, compute this cross entropy loss for us, which essentially is just the negative log likelihood loss in our case. So in our case, they are the same. So we can go ahead and take the negative log likelihood loss, which is have we imported it? Let's see, go back here, f.cross entropy input target weight, f.cross entropy, and then our input, which is p logits, and then our target, which is targets, and then the weight, which is the weights. So let's check this out, and we get around 3.53, which makes sense as we are computing the average of the negative log likelihood loss. So we are basically taking the minus log of p, and when we are freshly initializing our network, the vector that you are outputting should be basically uniformly distributed, since it's just random numbers. So we could just check what we expect it to be. So that's 1/21, as this is the probability of a softmax vector that's 21 long. So, and take the negative of that, and yeah, so we get pretty close to it. One difference is that we are using some weights for the classes, so that's why we maybe get slightly off, but it's in the ballpark. Okay, so the last term in the loss we have to compute is the box loss. However, here we have to notice that we will only compute this loss for boxes that has an associated label that's not the no label class. This makes sense intuitively, because if you predict a no class, then your bounding box shouldn't be taken into the loss because it doesn't count. So the bounding box can be arbitrary as long as you predict a no class. But if you do predict a actual class, then your bounding box loss will be taken into account. So specifically, what we are calculating here is the bounding box loss for all the predictions that actually got mapped in here to a ground truth. So what we'll do here is that if we go back to our matchings again, so again, I apologize, I should have used the seed here. But so for these indices, these predictions, they got mapped to ground truths. And therefore, we want to predict a bounding box loss for them. So, but this we've done before. So we can go up here to our matching cost, where we also compute a bounding box loss. So we can take this and copy it down here. And let's just make it obvious that we do bounding box loss. Now, the bounding boxes that we want to compute a loss over, we'll use this trick again. So we'll slice into our bounding boxes. Our bounding boxes are originally of shape, let's see, predicted boxes n and 4, so 104, and we want to slice into this. So let's just say the boxes from the permutation, so perm boxes, and we set those equal to whatever we named them, p boxes, and we also want these indices, as these predicted a actual class, and we refer to them as calls. So there we have our permutation boxes, and we can go ahead and uncomment this code again, and we want to convert these boxes, because remember the network predicts this format, but in the losses we expect this format, so we have to convert it. And we also have to make sure, typical copy pasting, the naming gets changed. So the boxes that we input will be the permutation boxes. We also want to keep that naming. Sorry. So let's do that here also. And let's see. The ground truth boxes for this will be the GT boxes here. So let's change the naming here as well. So let's just uncomment this for a while, and let's look at our permutation boxes and our ground truth boxes and their shapes. Okay, and their shape. So we see that we have, since we have n predictions here, and that's 4, it's 4 by 4, and so it's 4 on the rows because we have 4 ground truths, and it's 4, we have 4 columns because we have 4 coordinates defining a box. So previously in our matching cost, we only fed in one-dimensional tensors, but now it will be a 2-dimensional. But if we go into the documentation, we see that it can either be 1-dimensional or 2-dimensional, so this should be perfectly fine. And the same goes for the the L1 loss. So let's see the details here. Do they say anything about the shapes? Yeah, so any number of dimensions. So it should work here as well. So we can go ahead and compute the losses here. But one more detail when doing this is that here in our IOU loss, currently we use the reduction set to, let's see, so the default reduction is none, but we want, I don't know what it defaults to then. None, no reduction will apply to the output, because the output we want to have is, if we go down and see here, is the two losses are normalized by the number of objects inside the batch. So our batch size is 1, so our number of objects will be the number of objects inside the image. And since we do image per image, each image has number of ground truth boxes. So here we actually want to apply a reduction, which is a sum, and then we will average them later. Sum like that. And we'll also do that for the L1 loss. And now we will take our box loss and we will average it by the number of ground truths. So there you have it. That's our binding box loss. So now let's see if this runs. So let's print our box loss. Okay, I'm not going to try to interpret that. But now we have our two losses. We have our box loss and our negative log likelihood loss. And to recover this sum right here, we simply go ahead and we sum the losses. So our total loss will be our negative log likelihood loss plus the bounding box loss. And there we have it. So to summarize, given a number of ground truths and a number of predictions, which will always be 100, our boxes will be of this shape, 100 predictions with 4 coordinates to define a box, and then 100 predicted logits of size 21. We then go out to find a matching to map which prediction predicted the ground truth the best. And when we have this matching, we have now mapped each predicted box to each ground truth box to encode which prediction should be penalized for which ground truth in step 2 here. So now we can go ahead and encode the model. All right, so let's go down to the section 3.2 on the architecture of the model. The section is pretty good at explaining the architecture. They start with the backbone of the model, and then the transformer encoder, then the decoder, and then the feed-forward networks that make the actual prediction for the object. So in the introduction, they say the architecture is surprisingly simple, as depicted in figure 2. As we can see here, it's the backbone into the encoder, then the decoder, and then into prediction heads. So when implementing the model, we're really going to go step by step through this architecture. We'll begin with the backbone, then to the encoder, and then to the decoder, and finally the prediction heads. So let's go back to section 3.2 again. There we have it. So they say that in the backbone, they begin with an initial image, and then they use a convolutional neural network backbone to generate a low resolution activation map. And they have some typical values. So the convolutional neural network they use in their original code is this one right here. So it's the ResNet 50, which is a very popular backbone in object detectors and for classification as well. So when our image is first processed by the model, it will be fed in as input to the ResNet 50, and then we will use the output to go into the transformer encoder. Now, there are some changes we will have to make, such as the last layers at the ResNet 50, which are taking the last stage 5 here and then make it into a softmax vector, which is predicting a class. So these last layers we will have to remove, as the key idea with using a ResNet 50 is up until this point you have a really good representation of an image. So you have that your vectors here, they are representing features in the image that our encoder can utilize later. However, in ResNet 50, they are taking these representations and they are making them to predict a class for the image, which we don't want. We only want these features. So that's one slight modification we will have to make. So with that being said, we can go ahead and implement the backbone. So they start with an initial image, which is just 3 color channels. Okay. So let's go ahead and just do that. First, I will import some libraries that we will use. So we have torch packages such as their neural network and functional package. We also will import a pre-trained ResNet 50 model, and I'll also import a utils file that I've made myself that will come in handy later in the tutorial. So our image, let's see, we can just create some default values here. So they have a height and then width. So we have, let's just initialize the height and width to some typical values, say something like this. And we also want the image to be a tensor. So we have our image, let's define that to, or let's actually take random numbers. Like that. So let's see. So now our image is the expected shape to the backbone. So now let's see if we can pass this image through our backbone. So I will just copy paste our backbone in here. So this is pretty straightforward. So from torchvision.models, where you can access models, I will just import ResNet50 and have the weights from it being trained on the ImageNet. So now if we would just go straight ahead and take the image through the backbone like this, firstly we will get an error because it expected a 4-dimensional input and then we gave it a 3-dimensional input. And this is because when you feed the input into the ResNet model, it expects the input to be batched. So our input is good up until this point. So we have height and width and then channels, but we also want an extra dimension for batch so that you can process multiple images at the same time. So we will just have to add an extra dimension to our image, and that can be done by just using torch.unsqueeze, which is and then we provide an index. So then we just add an extra dimension at the beginning at index 0. And let's just verify that. So now our image is batched in a batch of size 1. Let's try again. And let's print the shape instead. So there we have it. So now, as we can see, the backbone is predicting a class for the image or a distribution over classes, but that's not what we want. So right now we have the full architecture. So our output is basically this, but we are interested in what's here. So one way of doing that is to use torch.nn sequential. So this is just taking a set of modules and then it will chain the input through the modules. So as they say here, the forward method of the sequential accepts any input and forwards it to the first module it contains. And then it chains the input. So I take my input into the first layer, I will get an output, and that output will be taken into the second layer. So basically, input here feeds into batch norm, frames into relu, and so on. So now we just want to get all these layers so that we can feed our input through it. So if we go down one block, we can say our new backbone should be so we first take the children of our backbone. So that is just returning an iterator over all these layers. And since it's an iterator, we can pack it into a list. So now we have a list of all the backbones. And since we now have a list, we can now take and remove the last layers of the list. So if I would do like this, for example, I would remove the last 2 layers. And why do I want to do that? If I were to say print the backbone, then we will get all the layers in the backbone. And as we can see, the last 2 layer is, okay, let's begin with the last one. It's a fully connected layer, which takes a vector of 2048 dimension in and outputs a 1000 dimensional out. And before this, we do a adaptive average pooling. So we take any sized input, and then we want the output to be of height and width 1 and 1. So this is basically taking a image of many channels and condensing it into just one channel, which we then run through a fully connected layer. So that's why we want to remove the last 2 layers, and we end up here. So let's go ahead and see here. Okay, so this will be all the layers up until this point. And let's wrap that into the sequential. And we will also have to expand the list into arguments, as we can see here. Okay, so now we take our sequential here of the modules of the ResNet. So we only take these modules, and we wrap that into a sequential, which will just pass our input through the modules. So now let's go ahead and look at the new shape. So first thing that comes to sight here is that the channels have increased, and also the height and width dimension have decreased. This is as expected if we go and see in the paper. So typical values for the channels are 2048 as we have, and we have the height and width here should be decreased by a fraction of 32. So let's just go ahead and verify that over 14. So yeah, that checks out. Now we have our image as they referred to in the backbone, and we can go ahead and look at the transformer encoder. Okay, so now let's get on with the encoder. So in the encoder, they say that they do a 1x1 convolution to reduce the channel dimension of the high-level activation map from C to a smaller dimension D. So they basically want to take this dimension right here, 2048, which is the channel dimension in our image, and they want to take that dimension and they want to compress it. In the paper, they use the dimension of 256, so that's what we're going to use as well. Now, the way that they do this is to do a 1x1 convolution. Now, some of you might find it strange that they do a 1x1 convolution, that you might think that it doesn't make sense to do like a convolution on just one pixel in the image and then move on to the other one. But what we have to think about here is that we have 2048 channels in our image, and those channels are operated on when we do a 1x1 convolution. So now, if we recall a convolution, when we do a filter of size 1x1, when we slide it over a pixel, that filter will have 2048 parameters plus 1 for the bias. So, and we will essentially apply each weight of the filter with each channel dimension. So it will be a linear projection of our channel dimension. We can look at this by an example. So here is an image. So in this example, it's 64 times 64 and a channel dimension of 192. And as you can see here, they extract one channel for one pixel in the image. And this channel is then projected into a single number. So they basically here do a dot product with the channel with a vector of length 192. So since we want 256 dimensions, we will have 256 filters. So we will do this operation 256 times, so that this block becomes 256 long in channel dimension. So let's go ahead and do that. So this is taken into account by Torch in their convolutional package. So we can just go ahead and use this. So here they have in channels, out channels, and kernel size. The default parameters, we can just leave them as is. So let's go ahead and implement this. So we want our projection to be nn.com2d, and our input will be 2048, and out we want 256, and our kernel size will be 1. So let's see if we got that right. In, out, and kernel size. Okay, so that will be our projection, and now let's see if we do this projection on the image. We want to see its shape. However, note now that I forgot to actually redefine the image here. So we have to do image, and then we can look at its shape. So that should be the same. And it is. And now after passing it through a convolution, here, let's see the shape again. Okay, so there we are. So now we've taken the channels. So for each pixel, there's a 2048 channel. We have done a projection of this into a 256 dimension instead. So let's go back to the paper now. So they do a 1 times 1 convolution to a smaller dimension d. Let's define this dimension for readability. So I'll call this d model equals to 256, and they go on and they say that you expect a sequence as input. So they collapse the spatial dimensions of set 0 to 1. Okay. So effectively now, the transformer expects just a vector, a one-dimensional vector that it can operate on. However, we have some spatial structure in our image. So we want to take our image and we want to flatten these two dimensions. But now we lose some positional context when doing this operation. So how can we cope with that? Later in the paper, they supplement it with some fixed positional encodings, so that when you flatten your image, you still want to add some context to each entry of the flattened vector that the model can use to infer the position of that token. Okay, so what I've done now is that I've cleaned up the cells a little bit. So previously we redefined the backbone and initialized it every time we would run these cells, but we want our backbone to be up here. and just have our image permutation in one contained cell to avoid some bugs. So let's just run all the cells, and we're working with our image, which now has its channels projected down, but we still haven't flattened the dimensions. So let's go ahead and do that. And verify it. So there we have flattened it, and now let's look at the shape here. The shape that we have now is our batch times, let's see, D model times our tokens. So now you can think of each patch in the image as a token, and the token is D model long. Now, one important note that we have to make here is that now our dimensions are D model times the number of tokens. But when we will feed this into a transformer, it will be a linear layer that is operating on it, and the linear layer will operate on the last dimension of the image it's fed in. And currently the last dimension is n tokens. So these are our image patches. But we don't want that. We want this to be transposed so that when we have it into the transformer, it will operate on the tokens. So we want the tokens to be on the rows, but currently they are not. So we will have to do a transpose here. The last two dimensions. So that we get it like this. So now our dimension is the batch, the number of tokens, and then finally the model. So now we have, when we go over the rows, that will be our token, which is corresponding to an image patch. So now this could be fed into a transformer, but as we have flattened the image, and the transformer is also a permutation invariant. What does that mean? Now, if I take the rows of this matrix, or tensor if you want, if I take the rows and shuffle it, the output will always be the same. So let me paste in some positional encodings. Now, if we would print the shapes of this, we have that the shape is 100 times 100 and 256. So what we have here is basically height times width for an image, and then the channel dimension here. This channel dimension is a positional encoding. So we have a 100 times 100 image, and each pixel is a positional encoding. So we want to add this to our image right here, but currently the shapes don't match. So what we can do then is just to slice the positional encoding according to our image up here after the projection. So that's what I've done here, defined the height and width of the image before we flattened it. So if we go ahead and set the positional encodings to be this slice, like that, and let's verify the shape. we see that we get the same dimensions as our image before we flattened it here. So we want to add this to our image. So let's go ahead and flatten the positional encoding as well. And we want to take the height and width here and flatten it. So we flatten the first two dimensions. And let's verify the shape. And there we go. Now, this is, let's see, is this shape correct? And tokens and D model, yes, but we missed the batch dimension. So let's add that one too. And verify the shape. And there we go. So now if we also print the shape of our image here, we see that the shapes match up. So now we have an image which is of shape and tokens times D model, and we also have positional encodings that's of the same shape. So what we can do now is to take our image and we can add to the positional encodings. Now the positional encodings, they are unique number that's unique for each position in the image vector. So now when we add this to the image vector and pass this into the transformer will learn to observe these patterns in the image vector. And thereby we are adding context to the image vector so that the transformer can infer when we do backprop and train the network, it can infer the position of the pixel. So now we have removed the spatial context, but then we add some information back into it that the transformer later can infer. So let's see if this concludes what we will input to our encoder. So we have done the 1x1 convolution, and let's see. Yeah, since the transformer is permutation invariant, they've supplemented it with positional encodings, and they defer to the supplementary material. So that's what we'll do next. So here is the transformer architecture. If you are familiar with the transformer, it's pretty recognizable. We have the encoder and the decoder with their attention and feed-forward networks. And one important distinction that we can make is that the positional encodings here, they are added to the keys and the queries, but the values stays unchanged. And we also have that they go into the decoder as well. So the way we will approach this is that we will begin here at the encoder, and then we will first encode the multi-head attention and then a encoder block. And then, as we can see here, they take these blocks and then they stack them onto each other. So the input of one block will be the output of one block will be the input of another block. So we'll get back to the stacking later. But first we want to see implementing a single head of attention. So to get better insight into the transformer, we can go to the attention is all you need paper, which is the original work on the transformer. We can go down to the model architecture here, and we see this is again very recognizable to what DETR has. But the key thing is that in this paper the attention is better explained, and here we really want to do the attention from scratch. So let's look at the multi-head attention here. So they say that the multi-head attention consists of scaled dot product attention and then concatenated. And this is really, imagine that you go deeper and deeper and deeper in the abstractions of the transformer. This is as deep as it gets, like a single head of scaled dot product attention. So this is what we will implement first, and then you can see it's used again in the multi-head self-attention, and the multi-head self-attention is again used here. So what we will do is like build these modules that we will later take into blocks that we can replicate. So it's really like Lego, that we will build the building blocks, and at the end, when we put them together, we will have the transformer. So the first thing that we will implement in code will be the scaled dot product attention. So specifically what we will do when implementing a single head of attention is essentially implementing this formula right here. So let's try to digest this formula. It takes in a query, key and value, and does a softmax over a matrix product, and then take a dot product with a value matrix. So essentially what we're doing is that, let's call this a score matrix. The score matrix will take a linear combination of the rows of V, and by doing that, average the rows of V. But what are Q, K, and V? So essentially, we start with one image patch. Now the image patch, this small patch in the image, is represented with a token that is D model long, that's 256. But into the attention mechanism, we want to just feed the raw token. What we will do first is that we will project this token into separate spaces. We will have one space called the query space, and one space called the key space, and one space called the value space. So when we get a raw token, we will project it into these separate spaces. So the query space will essentially be a query, something that you are looking for, while the key space is something that you contain or that you have, and the value is the value that you provide, the context that you provide. So this is how we allow the image patches to communicate. By having each patch emit a query and a key, you can have that different patches will communicate with each other in a way that is data dependent. So if one patch has a query that has a high dot product with the key of another patch, these two patches will get to communicate when doing the attention mechanism. So specifically when we are going to make this into code, we first have to take our patch and then transform it into our different spaces. So with that being said, let's define the different spaces. So we want 3 linear projections, one for the query, key, and the value. So let's go ahead and do that. And right now we just want a transformation between the same dimensions, so it will be D model and D model. And as common, we typically set the bias equal to false when doing attention mechanism. Like this, and let's be a bit quick and just duplicate it. Okay, so here we have our projections, and let's apply those to our image. So our query will be query of image. Now let's check the shape of this transformation. So as expected, the shape are the same as the image, as we can verify real quick. So these shapes are the same. However, what's happened here is that for each of these rows, for each of the 224 rows, we have applied a linear transformation. So the contents of the vectors are not the same. And there's also one more thing that we have to remember, and that is right here. So we also have to add the positional encoding to the query and the key. And intuitively, if you are in patch and you emit a query and you want keys to respond to this query, this spatial information is really helpful. Say that you like a hypothetical example. Say that you think you're the nose of a cat. Maybe you want to see if there are any ears that are peaky around you. So if there is some peaky shapes low down in the image, like far away from you, that's irrelevant. But if it's close to you, then it's relevant. So that's one hypothetical example of why we want to have positional encodings. So when doing a query here, we also want to add our positional encoding, which we defined here. So let's copy that and paste it in here. And we want to do the same for the key. But for the value, as we've discussed, we do not add any positional encodings. So that's it, and this should now run. Okay, so where are we now? So now we're at this stage. So we have our queries and our keys. So here they use uppercase, so it's denoting a matrix. So each row of this query matrix is a query corresponding to a image patch. So now what they do is that they take a dot product between the query matrix and the key matrix. And they also transpose the key matrix. So let's inspect these shapes. So q.shape and also k.transpose. And we want the last two dimension. We do not want to transpose the batch. And there we have it. So we have each row here is an image token, and we have that each column here will be a image key. So we have queries on the rows and then keys on the columns. So when we do a matrix product now, we have that the keys will be dotted with the queries, and they will compute a dot product resulting in a scalar. So like intuitively, if the query and the key has a high dot product, then we want to gather more information around those corresponding image patches. So here we want to take a matrix product with these two. So let's just define this as scores. And we have Q at K dot transpose. And let's check the shape. So it's now 224 times 224, which is expected because now you have the queries on the rows and the keys on the columns. So if you inspect one row of this scores matrix, it will be the dot product with that specific query with each of the keys. Now, furthermore, they go on to normalize it. So they normalize it by the square root of the dimension dk. Yeah, and that's the dimension of the queries and the keys. So they now take this matrix scores, this matrix right here, and then they divide it by the square root of the model. So they divide it by the square root of 256. So why do they do this? To answer that, we can look at a simple example. So if we go here and let's just say our dimension is 10, and we sample two vectors from a normal distribution. Like this, and then look at the dot product. So as you can see, the dot product is varying around 0 with around 6 and -6 in the tails, just running a few experiments. What happens if we increase the length? As we can see, the dot product is getting way bigger, or in other words, the variance is getting bigger. So why is this happening? Well, so we can assume that our queries and keys are sampled from a normal Gaussian distribution. So the dot product, each term in the dot product will be a one sample from a normal distribution and another sample from a normal distribution multiplied together. Now, if you increase the number of terms, then you can have that the values, like for each individual product, they can either be very high or they can be very low, or some can be high and some can be low. So that is making the dot product as a whole having a large variance, as it can vary between lots of different values. So to get a better intuition for this, let's go ahead and look at the distribution of this. So let's just say 1,000 dot products and look at the distribution of that. So then we can just do that into a list comprehension here. Like that. And this won't work now because it's just a list. So let's take it into a tensor. Okay, so our standard deviation is around 30. Let's run this a couple more times. Yeah, so it seems that 1,000 samples is more or less enough to get a representation of the distribution. But what happens if we decrease the length to 10, for example? Then we have that the variance is a lot smaller, which is because we have fewer terms in the sum when we take a dot product. So what happens if I would divide this by L? It's around 1. And if I would increase L to 1,000, we still have that it's around 1. So essentially, we want the variance to be the same for the entries in our score matrix, regardless of the size of the query and key vectors. And we see that we can achieve this by dividing by the square root of the dimension of the key. So we can go up here now and we can proceed. So we have done a softmax, and after having done a softmax, we can go further and multiply it with the value matrix, and this will be the output of the head. Okay, so and let's check the shape. Okay, so there we have it. So now effectively we have taken our tokens and we have let them attend to each other. And now we have this essential building block in place, and we can go further and utilize this block in later blocks. So let's go ahead. Okay, so what I've done now is that I've taken our previous code and I've converted it into a class. So here we have the code that we just did, and here is a new class that I've named encoder head. And as you can see in this class, we define the query, key and value projections, and in the forward pass we add the positional encoding to the query and the key. We leave the value as is, pass it through their transformations, and then compute the attention. And everything is like exactly the same as up here. However, there are some differences, and one of them is that as input argument, we still have the model. I've named it hidden dim here because that is what they do in their source code in DETR. And this one is new. So I've set n head to be 8. And this is the number of heads, which is the number of encoder heads that we want to do when we do parallel computation. So this is the next step when we follow the attention paper. So this is at where we are now, and we would like to get here. So as we can see, they take the scale.product attention modules, and they do h of them in parallel. So that is why I have n head set to 8 here. If we go further down to their section on multi-head attention, we can see that they have multi-head attention it's pretty straightforward. You have your h heads, in our case 8. You compute attention for each of them here, and then you concatenate them, and then you do one more projection. So, but one important note we have to make. So if we go down here, we see that when we did our attention first, we used the key inquiry dimension of a 256D model. But when we want to do this in parallel, we want to use a smaller dimension, and that dimension is set to be exactly our D model over H. So it will be 256 over 64. Sorry, it will be 256 over 8, which is 32 in our case. Here they say 64 because the model is 512 in their case. So what we're doing here in the multi-head attention is that we have 8 heads in parallel, and now instead of outputting a 256 dimensional token vector, we will only have 32 dimensions, and then each of these 8 32 dimensions, we will take these and then we will concatenate them into one dimension. Again, that is of size 256. So if we just run our encoder head for once here, so now the values are set to 256 and 8, which is what we want. So we will have 8 heads in parallel, and we also have to add our positional encoding in the forward pass so that it gets passed to the query in the key. So let's just define an encoder head. Okay, and we want to pass our image to it. And also the positional encoding. And let's look at the shape. So now we see, compared to what we previously did, we had 256, but now we have 32. So what stays the same is our number of tokens. So for each patch in the image, we have 1 token, and we have 224 patches in the image. And now we have a 32 dimension vector for the token instead of 256. And now what we would like to do from the attention paper here is that this is one head that we've computed, but now we want to do 7 additional heads. So we will have 8 in total of these, and then we would like to concatenate the values here. So the output then will be still 224 by 256, but the way we computed it is different. And the authors, they do this not by chance. If we go here, we can see that they found it beneficial to do it this way. So let's see if we can concatenate these heads. So let's go ahead and make a list of the heads. Let's do a number of heads like that, and then define n head to be 8. So now we would like to pass our input through each of these heads, and then we would like to concatenate this. So let's just define our values to be encoder head, image, and positional encoding for head in heads. There we go. So now we're essentially doing this computation right here, but we want to do it for 8 different heads. So if we go into vals now, our values, and check the shape of the first as expected. However, now we would like to concatenate each of these tokens, and we would like to do that along the last dimension, this dimension, so that we would reach our way back to the hidden dimension, the D model. And why do we want always to stay on D model? This is because these blocks will get chained, and we would like the input to stay the same throughout that chaining. So, okay, let's go ahead and do that. So let's go back down and concatenate the heads. Along the last dimension, like that. So now let's verify that we actually manage to get back to our initial D model here by printing the shape. And let's see, yeah, so that checks out. Okay, so now continuing with the paper. Now we've done the concatenation, and we're now going to do a final projection of the tokens. So let's just define final projection here. From D model to D model, and then we have and there we are. So now we have multi-head attention in place. So with multi-head attention in place, we can go ahead and define this in a class again. So here we have our encoder heads in a module list. So this list is the same as we have here, except that we have to wrap it in a module list so that when we call module.parameters, then the parameters of the encoder head is returned. If we would just have a list here, these parameters wouldn't be accounted for when we do model.parameters, which would be unlucky when we do backprop, because then we won't get to update these parameters. So furthermore, we have the projection layer here, same. And we're also doing the concatenation in the forward pass, followed by the projection, sorry. So basically all the same, just in a class. So now you maybe get the sense of we're like building these classes now together as Lego blocks. And if we look at the transformer again, it is starting to come together. So now we have this block right here as the encoder layer class. So what we can do now is to make this entire block. So now when we have done that, that will be a good milestone in our coding journey, because then the encoder will be basically in place. So what do we need to build this block? So the multi-head attention, the hard part we already have, but we are missing some residual connections, normalization, some feed-forward network. So let's go ahead and look at this feed-forward network. So in addition to attention sublayers, they say, each of the layers in our decoder and encoder decoder contains a fully connected layer. So it has the shape like that. So it's two fully connected layers and a ReLU between. And let's look at their dimensionality. So the input and output is D model, okay. And the inner layer has dimensionality 2048. So our D model is 256 instead of 512. So we will resolve this by having the hidden layer just 4 times D model, so 1024 there. So let's go ahead and now we will define all the modules that we need. So we can begin with the feed-forward network. So we have feed-forward network 1 will be just a linear layer from 256 to 1024. And let's see, yeah, they also have a bias here. And then we want to do a ReLU. So equals, let's see if I got the upper and lower case right for that one. Yeah, looks like we did. And the second feed forward. And then down again to D model. So let's see. First a projection, then ReLU, and then the second projection. So this should work. And then going back to the architecture, we have we also need 2 layer norms. So for this implementation, we'll use the layer norm implementation in Torch. This is also in the original DETR code. So really the difference here is that it's a layer normalization. So it's different from that batch normalization where we do normalization over the batches. So that's pretty straightforward to implement. We just input the shape or the dimension that we want to normalize over. And in our case, that will be D model. So let's just go ahead and define the layer norms. And the model, and same for the second one. And finally, we also need our encoder layer. Like that. So now let's verify that we have all the building blocks in place. So we have our layer norm up here. We have our multi-head attention block here. The feed forward modules and both normalizations. Okay, so then it's just to go ahead and write the forward pass for this. One important distinction that I will make is that instead of doing normalization after the forward pass through the attention, we will do it before. That's you can do both when doing attention, and I think there's not really that much that's changed about the transformer since it was released, but some things that people do different now is how they do the normalization. So we will do normalization here instead, so we will normalize before we pass the inputs on, and we will also do this with a residual connection. So let's go ahead and define x underscore res for the residual connection x. So this is really our branch out here, so that we'll be able to branch in again. And now we will pass x res through this stack right here. So we'll start by normalizing. And then we'll pass it through the encoder layer. And we'll end up here. So what we can do now is that we can branch in again. So we've gone through the stack, but we also have an x here that we can branch in again. So we just set x to be x plus x res, like that. So this leaves us at this point in the stack, and now we can just go ahead and continue. So we define x res again equals to x. We do second normalization over x. So x res, then we have the norm 2. And let's see, now we can pass it through our feed forward network stack. And ReLU. And our last layer. Okay. So, and lastly, we want to branch in again. Okay, so when we've finished through the attention stack, we get at this point, and then we branch out again. We pass it through layer normalization, through the feed forward network, and then branch in again. Once again, we are making this into a new block so we can continue building Lego. But as I was converting this into a block, I forgot to do a sanity check. So we could just do that real quick now. First thing to note here by our previous code is that we didn't define x. So, but obviously the intention was that x was the image. So let's go ahead and define that. And let's see if this runs. We get an error that the encoder layer is missing one argument, and it's the positional encoding. As we can see, the for pass needs to have the positional encoding in it, because that will be used in our attention nets. So let's add that. And let's see if it runs now, and we want the shape, not the vector itself. Pose encoding, that's because we named it pose encode, I believe. There we go. So we see now that passing the image through the stack, the original shape of the image, if we go here and check that, is the same shape as the output. So whatever shape we feed into the encoder block is the shape that we get out. And that makes us able to do a chaining of the blocks. So, but before that, let's just go briefly through the class of the encoder block, how it looks. So we are defining our encoder layer here. And just for fun, I implemented layer norm by hand here. I won't do this in the video in the interest of time, but it should work the same. Or in fact, I've checked that it does work indeed. So we have our layer norm here. So the second I didn't implement from scratch are fully connected layers. So the same thing here, we branch out into XRS and then first go through the encoder layer stack and then branch in again, and then we branch out and through layer norm and the fully connected layers. So now essentially, so this class is what we did here. So if you followed along here, this class should be really straightforward to understand. And now it really gets closer to our milestone. Now we have this entire block right here. And as we can see, the blocks are chained n times. And if we go back to the DETR paper, they also chain the blocks n times. So we can go ahead and do that. So we have our block here. Let's just define that. And then we can just say at our blocks should be so in their paper they are chaining 6 blocks, and there we have them. So when we have our input here now, we want to take our encoder block and we want to pass through all the encoder blocks. So we can just go for block in our blocks, and let's just define x equal to image here, and then we have image equals to block image. And now let's do the last sanity check for this. Positional encoding again, sorry about that. So I'm happy that that error came, because that leads me to here. So they have that positional encoding, they are added to each of the blocks. So we don't have it only at the first block, even though when we add the positional encoding to the image or the tensor and pass it through the first block, there is some information there containing position, but we still want to add it at each stage in the chaining. So adding the positional encoding here, and let's cross our fingers. Okay, there we go. So that should be our encoder block. Now here you have the last class of the encoder that I will copy paste into this code, and it's really straightforward. We just take our blocks here, I rename them as layers, define them up here, and on the forward pass we just chain the layers. And this class is now concluding our journey through the encoder. So now we're almost halfway there. I think the decoder is a bit longer. But now, having done the encoder like block by block, we will do this multi-head self-attention in a bit more efficient manner using vectorized operations. So let's go ahead. Okay, so let's go on to build the decoder of the transformer. I think for me, when implementing the architecture, the decoder was the most satisfying part to implement, because here you get to see attention at its best, because you have the queries and keys, they have different dimensions. And also when we'll gonna implement this, we see that we do multi-head attention 2 times. So the way we'll do this is that we will make a multi-head attention class. So in this class we will take in keys and queries and values, and then compute attention in one go, and then we can do this really efficient. If we go and have a look at the architecture, we see that the decoder takes a set of object queries. Now these object queries, you can think of them as detectives looking for different parts in the image. So specifically, you take a fixed size of n object queries, and they are basically just n tokens of dimension D model, which is 256. And then you will do attention between these queries and the keys. And now here we have that the keys, they are coming from the encoder. So the keys here, they are really telling something about the image. And you don't only get a key, you get a key value. So when you are doing attention between the keys and the queries, if a key has a high score with the query, then that query will get some of the image patch that corresponds to that, and that corresponds to that key. So this is illustrated here in the encoder. So the output from the encoder will be fed in here into multi-head attention as keys, and the values will also come from the encoder, so it's basically the same thing. And the queries, on the other hand, will come from the decoder. So it's really in this block that the magic happens, that the queries get to attend to the keys, and you are looking at different parts in the image. So since we have 2 attention blocks here, we will implement 1 attention block that we can use in both cases in other words, we can reuse it. So let's go ahead and code that. So if we scroll a bit up in the paper to multi-head attention, this is basically the module that we want to implement. Now it takes in value key inquiry, and we are going to assume that you have already added positional encoding to the keys inquiries, so that what comes in here can just be fed into linear transformations. So let's go ahead and define the queries. So the queries here, they will be of dimension the number of queries times the model, and we also will have a batch size 1 just for formality. Like this, and we also haven't defined n queries. So let's check. So there we have it, and we also have our X here, which is the image that we have passed through the encoder blocks. So we have that the shape of X is so we have the same dimension for the tokens, which is the model, but for the keys and values which come from the encoder, and we will have 224 of them compared to 100 of the queries. Now, one important note here is that 224, that is specific on the image, in other words, specific on the input. So if the input image would have been of a different dimension, this number would have changed. But as we'll see, the attention mechanism is independent of the number of tokens that's coming from the encoder. So now that we've defined the queries and keys, let's just make it crystal clear that we want the keys and the values to be equal to X and Q, K, and V. So there we have it. So this will be the input to our attention. So the first that happens in multi-head attention is that we want to have queries dotted with the keys. But remember now that this is for one head of attention. And in multi-head attention, we are concatenating multiple heads. However, previously we had multiple blocks that we concatenated together in another class and built it really like Lego. But now we will do it in a more efficient manner, so we have more parallelism in the image. So just stick with me for a moment, and then I'll explain as we go. So we are defining still our projections for the query, the key and the value, but now we will have the projection from D model to D model instead of D model to the head size. So we will not project down here. So let's go ahead and define those. And as usual, we don't set a bias. And let's apply these projections to our query key and value. And once more, to verify, let's print the shapes. Okay, so it's still the same shapes. So now we want to be really careful with our shapes and pay close attention to them. So I'm just gonna save them for reference or comment them out. So it will be batch size times enqueries times D model, and then we'll have again batch size, and then it's the number of tokens from the encoder. So the number of tokens is the number of image patches here, which is 224. This number, and then again the model. So what we'd like to do now is to encode different heads into the same tensor. So remember that we had n head, the number of heads, set to 8 in our example. So this is corresponding to h here, the number of heads. So it's basically the number of attentions that we want to do in parallel. And when we set n head to 8, since we're gonna concatenate the heads back again and then end up at D model, we have ultimately that our head size will be, let's see, D model over n head, which is 32, and let's do integer division there. So we end up at an integer. 32. So now we would like to encode 8 different heads into these tensors. So what we could first do is to have a look at the Q. So we have again Q.shape, which is enquiries times 256. But what we could do now is to have split 256 here into, we could split up 256. So consider this example, for example. If we have a one-dimensional vector that looks like this, we can call .view on it, like this, and thereby the numbers are staying the same, but we are changing the dimensions. So this we would also like to do here. So we take the token dimension, and we would like to chop up our token vector, and each slice, when we chop up the token vector, we want to be allocated to one head. So therefore we would like to have Q, and we want to view it in another way. Specifically, we want to view it as following. So still batch size of 1 here, and then we want, so now we have to pay attention here. We want our number of queries, and then we take n head, and finally head size. And now let's look at the shape. So we now end up with the following shape, which is the batch and queries and head, and then head size. And if we would manage now to get these two dimensions swapped, n head and n queries, we would effectively recover this matrix right here. So if I now go and q equals to q dot transpose, and we want to take the two middle dimensions, and let's print the shape again. Now we obtain the following shape: the batch size, the number of heads, the number of queries, and the head size. So as you can see now, that this single Q tensor basically has a matrix, which is the query matrix right here, and we have a batch of 8 of them. So since the attention is just matrix products, you maybe now get to see how we manage to do this in parallel. So if we want to chain our operation instead of having it over multiple lines, so the first thing we do is that we take q.view, and then we do dot transpose, and this is the same as that. Let's check out the shape to be sure. Okay, because here we did it multiple times, so let's comment out this and try again. So there we go. So we have the batch size, the number of heads, the number of queries, and the head size. So now we will do the same for the key and the value. So let's just do the same operation to the key and the value. So we define their transformations here, and then we take and actually apply the transformations. So for the key now, we will also view that as the batch size, but then we won't have the number of queries, we will now have the number of tokens. So let's define that up here. Tokens equals to k dot shape 1. We will verify this afterwards when we print the shapes. So n tokens, and then n head, and then head size, and we do a transpose. Okay, I did type that right. 1, 2, and this should be the same, but now n tokens. So let's verify that shape. Okay, so we had uppercase, which should be lowercase. Okay, so there we go. As expected, we had the batch size, which is 1, and then the number of heads 8, the number of tokens, and then the head size. And let's go ahead and do the same for our value here. So let's just duplicate this line, as the dimensions are the same for the keys and values, like that. So, okay, there we have it. Now that we have encoded the different matrices into the tensors, we can go ahead and do this operation right here in parallel. So as we can see, for each of these dimensions, if we just keep these fixed, we have n queries times head size and n tokens times head size. And that is the query and the key matrix in the attention operation. So now we would like to do this for all of the 8 heads in parallel. And since we have them nicely stacked up in tensors with these shapes now, that's pretty straightforward. So if you notice now that we can actually go straight ahead and compute scores as Q times K, where we transpose the last 2 dimensions. Because if we have a look at this dot product, we can see that this is, okay, I think we need a new line for it. So this is dimension of Q, the query, and then we have dimension of the key. But now the last 2 dimensions are transposed, so we have head size here and number of tokens here. And now you can see that when we do a matrix product here, that will apply to these matrices. And you see now, since this is transposed, they matched up between the bridge of the head size. So each dot product will be of length head size, or the vectors that we dot with each other, they are of length head size, which is perfectly as expected, because in each of the individual heads, the vectors are of length head size. So if we go ahead and do this, we have that the result will be the batch n head, so this stays unaffected, n queries, and n tokens. So what we end up with now is this matrix products. So for each row here, so we have the queries on the rows, and so for each row you have a query that is dotted with a key, and that is for each head in the dimension here. So we can just continue following the formula here. So we have done this matrix product now, and we can go ahead and normalize it, and we still want to normalize it by the head size, because the matrices are still of so the dot products for each entry in the matrices are still a dot product that was computed from vectors that were of dimension 32 or size 32 long, whichever you prefer. So we can go ahead and normalize scores by the square root of head size as we've defined up here. So when we've normalized them, we want to take the softmax, and as before, we want to take the softmax over the rows, which is the last dimension here. So let's go ahead and take the softmax over the last dimension. Like that. And now our scores will still have the the same shape here. You can also verify that. So batch size, number of heads, number of queries, and number of tokens. And what we now can go ahead and do is to do a matrix products between the scores and the values. So let's just see what this will look like. Sorry. So scores will be of this dimension, and then we have that the value will be of this dimension. So our results then will be b and head, and then let's see, n tokens will bridge them, so we will have n queries and then head size. So that will be our output. However, there is still some more work to do, because if we expect the dimensions here, we have n head times n queries and the head size, but we would like to this to be, so let's say we would like b n queries and d model. So now we want to go back in the same format as our input were. So let's think how we can do this. So the first thing we would like to have is the queries to get over here. So we want to switch dimension with the number of heads. So we can do out is out.transpose, and we want to transpose the middle dimensions. So it's 1 and 2, and let's check the shape. So okay, so now we have n queries here, and what remains is the model. So here we have, so let's examine this shape. So we have our batch size, n queries, and then n heads and head size. So if we would flatten these two last dimensions now, we would recover our original model dimension, 256. Dot flatten we want to do, and then the last two dimensions. There we are. So the last thing remaining now, after having gotten back to the original shape, is to apply a final transformation. So let's define that. To be just a linear layer, and have that to be d model times d model, and no bias here either. And we can apply that transformation. And there we are. So there we have it, the scaffolding for a multi-head attention. Okay, so what I've done now is that I've taken the multi-head attention that we did in a notebook, and I imported it into a script here. So as usual, everything is the same. So if you followed along with the notebook, this should be very easy to understand. Only difference is that we define our linear layers appear, and we call them in a forward pass, but the math is basically all the same. I've also done this for our other modules that we did, such as the encoder, encoder block, encoder layer, and the encoder head. Now, furthermore, the decoder block we haven't seen before. We want to do that one in a notebook because it's basically just calling a bunch of modules, and I think it's best to see to go through and go along with the architecture as well. So the decoder block is the last block in the transformer. So let's see what it does. So we do we initialize a layer norm, we initialize multi-head self-attention, another layer norm, multi-head self-attention, layer norm, and then feed forward. And that's corresponding to multi-head self-attention, layer norm, multi-head self-attention, layer norm, feed forward, and then layer norm again. So we see that in the decoder we have two modules of multi-head self-attention, and we have three layer norms and one feed forward network. So once again, we will do the normalization before here. So in the forward pass, we will do a layer norm. We will add our positional encodings and pass it through a multi-head self-attention. So now we are here. And now this is the interesting part. We do cross attention. So now our queries, they will come from this self-attention block. However, our memory here will be the output from the encoder. And output from the encoder comes here. So this is our memory and feeds in as keys and values. So that's what we see here. And we also add the memory positional encodings, which are the positional encodings I introduced earlier, which come here, that we add to the keys. And yeah, I forgot to say, we also have some positional encodings for the queries, and that's what we see here. And these are learnable parameters, so we see when we define them. Okay, we will define them later. But these are learnable embeddings. That's what we see here. So these object queries here will be initialized as 0 initially, and we will add query positional encodings to them, so that over time they will learn to look at different patches coming from the encoder, which we refer to as memory. So in the cross attention, the difference is that the keys and queries and values, they come from different sources now. So we do multi-head cross attention, and that's basically just calling the multi-head attention block that we just did. And then through a feed forward network that should be familiar by now, and then returning it. So that is the decoder block. So now it gets easier to understand this whole architecture once we wrap it into a final class that calls all the modules. So it's really a lot of blocks here. So the inputs here, we have our backbone. We expect that to be a ResNet 50. And then I have this parameter, which I refer to as, when we do positional encodings, what is the maximum height and width of the positional encoding that we want. So in our example, our image was 14 and 16 in height and width, and we set the positional encoding that it cannot operate on images that are more than 100 in height and width. So for our 14 and 16 image, this works perfectly fine and should generalize pretty well. So our number of layers is basically this n and m here. It's the number of times we want to stack the block up on top of each other, so it's the length of that chain. So that chain is 6 in length. Then it's the number of heads, which is the number of encoder heads here that we do in parallel. So we can go to the transformer paper and let's see if we find that. So our number of heads will be this h here. So we set that to 8, as that is what they do in the transformer paper as well. Our hidden dimension, that will be the dimension of the vectors that we pass along in our transformer. The number of queries will be the number of object queries here. The number of classes will be the number of classes that we will predict for an image. So that goes into the class feed-forward network here. So what's the length of the vector that we want to output? And then we do a batch size of 1 to just keep this like as an educational exercise and don't get too confused with batching. I think it improves the readability to have that set to 1. So we, as we've seen, we have our backbone, we initialize that, and we remove the last 2 layers because we don't want to do classification here. We want to do feature extraction. And then we define our projection to go from 2048 to the hidden dimension, which is set to 256, and column size 1, of course. We get our sinusoidal positional encodings, which is the positional encodings that we used earlier. So, which gives us this 100 by 100 times 256 matrix. So, and also we register this as a buffer because these are not parameters that we want to learn. These are just numbers that we want to apply to during inference in the transformer. We then define our encoder block that we looked at earlier, and then we build the decoder. So we take our number of queries, which is set to 800, and then we define, so here it comes. Here we do, we define a parameter, which is set to be just random numbers at the beginning. So these are our initial positional encodings for the queries, not the image features, but the queries. So it's the positional encodings for these. And these are first set to just number of queries times hidden dim, so 100 times 256. And so this is a parameter, so these will be learnable. And then, as we've seen before, we just take our decoder blocks and we wrap it into a module list because we want to access these parameters during training. So we have just end layers, which is 6 of these that we have into a module list that we will pass our input through. And then finally, we add our prediction heads on top here. So this is just a feed-forward network. So when you get your output from the decoder, which is your queries, so that will be of the same dimension here, number of queries times hidden dim. So this will be the output of the decoder, and it will also be the input to the decoder when you chain it. So that will be hidden dim plus number of classes, and notice here that we do +1, and that is because we also want to give the transformer the opportunity to classify an object as no class. So that's out of distribution. So if it's an object that it hasn't been trained on before, it has the opportunity to be classified as no class. And then if you do that, your bounding box will be ignored when you do a prediction. So this is really helpful since you always do 100 predictions. You don't typically have 100 objects in the image, and then you want some of your bounding boxes to be ignored. Then we have our feed-forward network for the box. So we have one head to predict the class here and one head to predict the box. So what's really unique here, so this is also just a feed-forward network. So what's really unique here is that for the same token of length 256, you use that token to predict both a class and both a bounding box. So really this encoding is, or this token is encoding knowledge about what class is this and where is the bounding box, or what's the coordinates of the bounding box. So there's a lot of information encoding into this 256 length vector. So now let's look at forward pass of the transformer. So firstly, we do a pass through the backbone of our image. So this we've already seen in the notebook. Notice here that we do torch.nograd, and we do this because this is supposed to be a simple model, so we don't want to do backpropagation through the backbone as well. We just keep that as freezed. The backbone has been trained before and is already a reasonable feature extractor, so we don't have to do training there as well. So in the original paper, they do train the backbone with a very small learning rate, but here we won't do that, and we will see that that works perfectly fine as well. So we do our projection from 2048 to 256, and then just a small assertion here that our image is not exceeding what our positional encodings can operate on. We flatten our image such that we get tokens times hidden dim. So every row here will be a token of length 256, which is our hidden dim or D model. So let's go on. We have our positional encodings that we create. So this we've seen before, that we just slice and then flatten and then unsqueeze so that we obtain this shape right here. So height times width, that's also the number of tokens that we have. So we define our encoder. This class we've seen before in the notebook, so that's basically just the same. We initialize our queries. Our queries is the input to the decoder here, so they are originally just zeros. They don't know what to look for yet, but as you can see, when we pass them through our layers, our decoder layers, so the queries goes in there, and they also go out, and then they go in again. And then you can see, then we have added information to them. So we initialize them as zeros, but over time they will learn reasonable representations to do attention with the encoder memory that comes in. So here's a sanity check that I've left out to check the pre-activation for the distributions, to just check that the gradients actually flow through the network, and that we stay in a good region of the activation function. So, and that's our whole model. Okay, so I'm now importing the DETR class that we previously looked at, which is really like taking all the modules that we've created throughout this video, importing that class here into a main file, which is a script, basically a training script. So the datasets that I will use will be VOC, also goes under the name Pascal. A dataset for object detection was released in 2012, has a bit less than 6,000 images for training. And it was a common dataset before Cuckoo, I think. So that's the dataset that I will be testing the model on. So some transforms that we do to the data is basically that we just normalize it according to the ImageNet statistics. So here we have our loss that we looked at earlier. And here is, first, just for a sanity check, I am creating a small dataset containing only 2 indices of the dataset, and just to check for some bugs, I would like to see if we manage to overfit first. So the script itself is pretty straightforward. We define our backbone, our DETR. Here we just print the parameters, and we have the ADAM W optimizer with a learning rate of 3 to the negative -4, with weight decay as well. And then we will do a step for every 75 epochs, because our batch size will be only 2, because we only have 2 samples in the dataset that we will do 200 iterations on. So what we'll do is that we will go through the batch. So this will just run for 2 iterations. So we will get our image and target, and we will run the image through the model. And this is the model that we have made ourselves. Run the image through the model here, and then define the loss. We define a epoch loss up here. So for all the samples in the batch, we just calculate their loss and then add it to the epoch loss. And then when we've iterated through all the batch elements, we will average the loss, and then we will do backpropagation on it. So when we run the script, we see that we start up at 7.5, and quite drastically we get down to 1.6. So what you can note here is that the class loss is adapting pretty quickly, but the bounding box loss is what takes time. So we can go further down. The class loss is very close to 0, but the box loss takes still some time. But we can see that after, say, 150 iterations, you start to get really close. And at the 200 iterations, we have basically overfit. So yeah, that's a small debugging tool we can do to just sanity check ourselves if the model is doing as expected. So I also wanted to see how good this model can generalize. So for our training dataset, which had a bit less than 6,000 images, I would train our model on this dataset for 10 epochs. Each epoch took around 13 minutes. So not that much training really. It's just above 2 hours. And what we can see here is that I have saved the model for each epoch. So this is the last epoch that we did. And if we want to calculate a common metric such as the mean average precision, which measures how good your boxes align with the actual objects in the image, we see that it's pretty terrible, but that's expected due to just a few hours of training. Keep in mind that we haven't done any cropping or augmentations to the images or done some feature extraction. So we've just taken the data set of less than 6,000 images, and that's what the model has to learn from. So yeah, very limited data set and also very limited training time. The original model from DETR, it trained for, yeah, we could actually go see how much it trained for. I think it was quite a lot. So let's see. If we just type in GPU, maybe it appears for us. Yeah. So let's see. Training the baseline model for 300 epochs on 16 V100 GPUs takes 3 days with 4 images per GPU. So that is, and they also, yeah, batched. So that's, yeah, it really can't compare to the training we did. And also for their mean average precision, they got around 4.2. Maybe we have that here. Let's see. So, okay, so they do some comparison on the Cuckoo validation dataset. So they got an AP of 42, where we got not that much. We had 1.5 or 1.6. And the AP50 that I got was 62, while we got 4.36. However, this is supposed to be an educational exercise, so if we would just keep training this model, I believe it would get better, because when I trained it, loss would just keep going down. It was no signal that it would stop, but in the interest of time, I wouldn't let it run. And what's interesting here is that this is for 9 epochs. If we see the model that was after 5 epochs, so after training for 5 epochs, just save the model and now see how it performs, we see that it's a lot worse. So for mean average precision at 50 intersection of union, we got 0.04 here, and here we got 0.01. So it's a drastic decrease. So we see that the model gets better with more data, which is a good sign. And also more training, of course. And if we just look at 1 epoch of training, then it's just complete garbage. So this is like, we've done 2 important sanity checks now. We see that it overfits, and we also see that it gets better with more training. So I would encourage to train this model for more hours, but I won't spend my time doing that. It could also be interesting to see how it looks if we visualize it. So what does the predictions of the model look like? So here we have just printed the model's predictions at the validation dataset. So this is like unseen images for the model. So at the left here we have the predicted box, and on the right we have our ground truth. So we see that it predicts a bicycle with the 0.8 confidence when it should be a TV monitor. Let's see. And now I gave it 10 samples to predict on. So for samples 1 to 6, it didn't predict anything at all. It would just output no prediction boxes. So that's reasonable. It's just outputting R class 21. But for sample at number 6, we see that it is actually recognizing that there's maybe a person in this image. So it's not sure where the person is, and maybe thinks that it's more persons, but you can see how it captures, first of all, the class, but also the dimensions of the box. So it manages to capture the height of the box, but not exactly the width. So we can go on further on. Here, it's a car originally, it predicts a motorbike, but in the ballpark, the same. And for the bus, it actually gets it correct, although it has a bit low confidence score. So, okay, that's the end of this video. I really appreciate some feedback if you have some, and I hope that the takeaways of this video is the educational aspect of it. The goal was not to create a model that's beating the benchmarks. It's rather to for you as the viewer to get more knowledgeable about what's happening under the hood of object detection methods. And I think that we did that in a nice way with just 100 lines of codes and a lot of insight into how this milestone model DETR worked. So thank you for sticking with me, and maybe see you next time. Goodbye.